Okay, now that we've learned about logical propositions and about operations and equivalences, now let's look at some applications of this propositional logic we're learning. So as I've mentioned before, one of the main applications for this is circuits, circuits in a computer. Computers perform logic all the time, very quickly, and they do that using basically wires that carry signals, and that signal is a binary signal. It's what's called like a a digital signal. It's on or off, 1 or 0, true or false, and then it's those signals are combined in what are called gates, logic gates, and those logic gates are performing logic operations, and then they're sort of combined together in different ways to evaluate different compound propositions in order to do things, do everything that a computer does. So we're going to study this. Now, in order to understand what a circuit is doing, we need to be able to translate between a circuit diagram, a symbolic representation of a compound proposition, and a verbal statement that describes what it means. So let's go through those three things. We're actually going to start with the verbal statement. Like, let's say it's the ball is red or blue. That would be a example of a proposition expressed verbally. That can be translated into a symbolic statement. So for us, that's going to be the ball is red or the ball is blue. So I'll represent that as R or B, like that, where R and B would be propositional variables representing the two propositions, the ball is red and then the ball is blue. And then we can translate that symbolic statement into a circuit diagram where we have signals corresponding to the truth value of each of those propositional variables. So we have like a wire carrying some electric current, which is corresponding to the truth value of R, and a second wire carrying an electric current corresponding to the truth value of B. Okay, so that would be on or off, carrying a 1 or a 0 bit. And then these get combined using a logic gate. And the logic gate is actually some sort of thing that's built out of transistors, so the electric currents get combined in certain ways, and I don't really understand all the physics behind what's happening inside there. To me, as a mathematician, it's just a logic gate. Two signals go in, and then this is the gate that represents the OR operation, and what comes out on the other side is the truth value of the R or B proposition. So I've laid them out in this diagram in this direction because this is how you would design a computer, right? Like, this is obviously a super simplified version, but the idea is you want to understand, like, verbally what it is that you want the computer to do, right? And then you can represent that symbolically. This gives us a stepping stone on the way to drawing a diagram of a circuit. And then, of course, the next step after that would be to actually build the circuit and deal with all the hardware issues that come up in building circuits. Like, there's lots of hardware issues that come up in building circuits. But we're going to focus on these three steps, translating from and translating back and forth between these, but mainly going this direction, translating from an idea to a symbolic statement to a circuit diagram. So in order for us to do circuit diagrams, we need to know what the logic gates are, and we need to establish our logic gate symbols. We're going to make circuits with just 3 types of logic gates. So the first one is a NOT gate, also called an inverter. This is for the negation operation. You take your propositional variable P, so you have a wire carrying that signal on or off, 1 or 0, and then it goes through a gate that looks like that. So that is your inverter, and then what comes out the other side is not P, like that. So that's not. Then we have AND. So we have P and Q, whatever our two variables are, and the AND gate is a straight line with a hemisphere on this side, or hemisphere, sorry. We're in 2 dimensions here. It's a semicircle. And then what comes out over here is your P and Q. That's our AND gate. And then we have the OR gate. And I always think the OR gate looks, it's this thing. It looks kind of like a spaceship. It's like blasting off. There it goes. It's P or Q. So those are our 3 logic gates that we'll be using. And we're going to create circuits out of those things, combined in different ways.